Good day, everyone, and welcome back to our pre-calculus class. Last time we were looking at the concept of double angle. Let me quickly show this. We derive these identities for double angles. And now we want to use this idea to come up with some other identities. So I will start. Sine of 2 theta is 2 sine of theta cosine of theta. I'm just rewriting what we already derived. And this is cosine squared of theta minus sine squared of theta, which is the same thing as 2 cosine squared of theta minus 1, which is the same thing as 1 minus 2 sine squared of theta. From these identities, we can do something interesting. So from 2 cosine of 2 theta equals to 2 cosine squared of theta minus 1. So this is our double angle formula. Okay, so picking cosine of 2 theta from there, I can rewrite this as 2 cosine squared of theta minus 1 equals to cosine of 2 theta. That is allowed. And I can say 2 cosine squared of theta is 1. That is, I can add 1 to both sides. So plus cosine of 2 theta. And now I can divide through by 2. So I have cosine squared of theta equals to 1 plus cosine of 2 theta divided by 2. So I call this a reduction formula for cosine squared of theta. Also, from cosine of 2 theta equals to 1 minus 2 sine squared of theta. I can do the same thing. So I will have 2 sine squared of theta equals to cosine of 2 theta. And I can say, well, minus 2 sine squared of theta equals to cosine of 2 theta minus 1. I can divide through by negative 2. So I have sine squared of theta equals to, so if I divide this by negative 2, I will have negative cosine of 2 theta plus 1 divided by 2 because I divided by negative 2. So the signs there will change. Okay, now I can say sine squared of theta equals to 1 minus cosine of 2 theta divided by 2. So that is a reduction formula for sine squared of theta. And now, for tangent squared of theta, we can do the same thing. We can say this is well, sine squared of theta divided by cosine squared of theta. And in the end, we will be having 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. So these identities are called the reduction formulas. So sine squared of theta, for cosine squared of theta, and for tangent squared of theta. Why do we have to do this? There are some situations whereby we will have something like this, maybe sine raised to power 6 of x, or sine x raised to power 6. we need to reduce it. We need to be able to reduce it in something we can, handle. For example, when you get to calculus class, you will be working on integration, or you will be dealing with some trigonometric functions that requires you to reduce them to something like this before you can go ahead with your uh, solution. Okay, so having known this, again, you do not need to memorize this. This will be provided if need be, or you can just put it on your uh, cheat sheet. Okay, write an equivalent as an example for the following expressions that does not involve any powers of sine or cosine greater than 1. Put differently, we are saying reduce this to cosine or sine that is not more than power of 1. So, looking at this, I can say this becomes cosine squared of, okay, let us do something. This same thing means I can write it as cosine of x raised to power 4, which is the same thing as cosine of x raised to power 2, everything raised to power 2. So, which is the same thing as cosine squared of x raised to power 2. That is fine, I believe. Now, we know the reduction formula for cosine, and that is 1 plus cosine of 2x divided by 2, everything squared, using this, right? Using this formula. That is the reduction formula for cosine. Now, I'm not done because I still have power of 2. So I need to be able to break it down. So this is, let me be careful. I can write this as 1 over 2, 1 plus cosine of 2x, everything squared. Just bringing that out. Okay, now if I use that square on it, I will have 1 over 4 into, if I have 1 plus, let's see, if I have a plus b, everything raised to power 2, it is the same thing as a squared plus 2ab plus b squared. You should know this by now in your head. So if I apply that, here I will have 1 plus 2 cosine of 2x plus cosine squared of 2x. Again, I'm not done. How do I know? I still have power here. So I need to deal with that. But before I move on, I can open up and I have 1/4 plus 2 over 4. That is 1 over 2 cosine of 2x plus 1 over 4 cosine squared of 2x. So I know I need to deal with these parts. So this is equal to, at this point, I do not have problem with all of this again because there is no power on that cosine. So that is fine. It's the same thing, no difference. Plus 1 over 4, then I do know that cosine squared of x is 1 plus cosine of 2x divided by 2. However, instead of x, I have 2x there. So I need to replace this x here by 2x. So that is 1 plus cosine of, instead of 2x now, I will have 2 of 2x divided by 2. Let me show you again. from the formula, I have that the reduction formula for this is 1 plus cosine of 2x divided by 2. However, my x here is, when it is 2x, so here I need to write 2x there. So that is what I've done. So this is 1/4 plus 1 over 2 cosine of 2x plus 1/4 into, again, 1 over 2 into 1 plus cosine of 4x. So that is 1/4 plus 1 over 2 cosine of 2x plus 1 over 4 into, if I open up that, that is 1 over 2 plus 1 over 2 cosine of 4x. And that is, so this is equal to 1/4 plus 1/2 cosine of 2x plus 1 over 8 plus 1 over 8 cosine of 4x. And we are done. Well, maybe I can add this and this. So that should give me 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. So guys, that is where I'm going to stop, because the power of cosine here is 1. The power of cosine here is 1. So I stop. So I have been able to reduce that function. Therefore, cosine raised to power 4 of x is the same thing as 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. Let us take another example. Again, notice that I can write this as sine squared of 2x multiplied by sine of 2x. In fact, there is no problem with this part again, because the power there is 1, but we still have raised to power 2 here. Okay, now the reduction formula for sine squared of x is 1 minus cosine of 2x divided by 2. However, instead of x here, I have 2x. So instead of x here, I will have 2x. So that becomes 4x. So I have 1 minus cosine of 4x divided by 2 multiplied by sine of 2x. So this is, I can leave my answer that way, because everything now is in power of 1. So there is no square anywhere again. I will just leave it that way. There is no need to do more. Okay. Now, another thing we want to look at is the half angle formula. And I will derive the half angle formula also from our work with reduction formula. So recall, we want to recall that sine squared of x is 1 minus cosine of 2x divided by 2. Also, cosine squared of x is 1 plus cosine of 2x divided by 2. Now, I can do something. If I say let x be maybe something like alpha over 2. Alpha over 2. Let means I just want to do that. So that implies that alpha equals to 2x, right? So I can replace wherever I see x, I can replace it with sine squared of, instead of x now, I write my half angle there, equals to 1 minus cosine. Instead of 2x, I will put alpha, right? From my representation, divided by 2. Therefore, sine of alpha over 2 becomes plus or minus square root of 1 minus cosine of alpha divided by 2. So that is the half angle formula for sine. And for cosine, again, I do the same thing. Let x be alpha over 2. So that implies that alpha is 2x. And the cosine squared of, instead of x, I write alpha over 2 equals to 1 plus cosine of, instead of 2x now, I write alpha from here, divided by 2. And now cosine of alpha over 2 is plus or minus square root of 1 plus cosine of alpha over 2. So I call this half angle formula for sine and cosine. And again, we can do the same thing that we've been doing for tangents, just divide those results with sine by cosine. Now, in general, we have this result. Sine of alpha over 2 is this. We just find it. Cosine of alpha over 2 is this. And to compute for tangents, just divide our results, sine by cosine, and we end up having this. So this, again, are half angle formulas. Why do we want to do something like this? Remember, on the unit circle, we have been able to find values for the special angles. And then we said, okay, maybe something like 30 degrees, 60 degrees, 45 degrees. We're able to find those terminal points. But then we say there are some angles that we cannot find. For example, let's say 15 degrees. Then we say, okay, we can use the idea of sum and difference of angles. Then instead of saying we cannot use unit circle to find it, we say, okay, for sine of 15 degrees, well, we can use something like, say, 45 degrees minus 30 degrees. And we can use sum of angles or difference of angles. The same thing, we can also say, well, 15 degrees is also half of 30. So we can use half angle as well. So your question might be, which one should I use? Anyone you remember, anyone you are comfortable with, because you will get the same results. Okay. All right. Now, let us find sine of 15 degrees using, like I said, half angle formula, because we can use other method without calculator and we still get it. But we want to use half angle. So I can say let's alpha over 2 be 15 degrees, right? Half angle. Let it be 15 degrees. That is, there is some angle. The half of it is 15. So that implies that alpha equals to 2 times 15, which is 30 degrees. Just like I did when I was deriving the formula. Now, sine of alpha over 2 is plus or minus square root of 1 minus cosine of alpha over 2. That is using this. Now, I will say that my, because 15 degrees is in the first quadrant and sine is positive there. So I will stick to positive. Now, so this is sine of 15 degrees because alpha over 2 is 15 equals to square root of, in this case now, I have 1 minus cosine of our alpha is 30 degrees divided by 2. So that is square root of 1 minus cosine of 30 degrees from unit circle is root 3 over 2. So divide by 2. And that is square root of 2 minus root 3 over 2 divided by 2. By solving the numerator, you get 2 minus root 3 over 2. Then divided by 2. So, which is square root of 2 minus root 3 over 2 times 1 over 2, because this is 2 over 1. And that is square root of 2 minus root 3 divided by 4. Remember, if I have square root of a over b, I can write it as square root of a divided by square root of b. So meaning that I can say this is square root of 2 minus root 3 divided by square root of 4. And that is square root of 2 minus root 3 divided by 2. And I will leave it that way. So that is our answer. If you find sine of 15 using your calculator and you keep it and you evaluate these results, they will be the same thing. They will be the same thing. Okay. Let us solve more examples. Given that tangent of theta alpha is 8 over 15 and alpha lies in Q3. With that, we know that we can do this. We have encountered situations in this class that we now know what to do. So tangent of alpha, that is opposites over adjacent 15. Let's say we do not know this length. Call it question mark. We can find question mark squared by adding the squares of these lengths. So this is 225 plus 64. Question mark squared is 289, and question mark is square root of 289. Can say plus or minus, so that is plus or minus 17. Well, I will just write 17 because I have other ways to deal with the signs. So I compute that. Now let us find sine of alpha over 2. Remember that sine of alpha over 2, we cannot use this directly because this is alpha, not alpha over 2. But we do know that sine of alpha over 2 is plus or minus square root of 1 minus cosine of alpha over 2. The first thing we need to deal with is the sine of alpha over 2. Now, our angle alpha lies in Q3. Let us write it in interval form. Q3, that is here, right? That is between pi and 3 pi over 2. So I can say pi less than our angle alpha less than 3 pi over 2. However, the angle I'm looking for is alpha over 2. So I need to multiply through by alpha by half. So this is pi over 2 less than alpha over 2 less than 3 pi over 4. So this is 90 and this is a 135. So 90 and 135 is somewhere in this second quadrant. So meaning our alpha over 2 is in the second quadrant. And what that means is that sine is positive there. So our answer should be positive. Now equals to square root of 1 minus cosine of alpha. We need to be careful. What is the sign of cosine of alpha? Cosine of alpha, this is where we have alpha. So cosine of that is cosine of alpha is adjacent over hypotenuse. So that is 15 over 17. Is it plus or minus? Alpha is in Q3. Alpha itself is in Q3 and cosine is negative there. So we have minus A divided by 2. Try to make sense of that. So we have square root of 1 minus times minus plus 15 over 17 divided by 2. And that is 17 plus 15 over 17 divided by 2. Divided by 2. And that is square root of 32 over 17 times 1 over 2. So I can say 2 year 16, 2 year 1. So that is square root of 16 over square root of 17. So like we did the other time, this is square root of 16 over square root of 17, which is 4 over square root of 17. I can rationalize this. We have done this several times because we do not want the square root to be at the denominator. So our answer is 4 root 17 divided by 17. Let us go to the next one, cosine of alpha over 2. Cosine of, okay. Move you. Okay. So now, the next one is cosine of alpha over 2. Again, the formula is plus or minus square root of 1 plus cosine of alpha divided by 2. Now, the first thing we need to decide is what is the sign of cosine of alpha over 2. We have done it here. We realize that alpha over 2 is in Q2. And that means that cosine is negative there. because cosine is negative in second quadrant. So um our okay. So we are dealing with negative there. So equals to minus square root of 1 plus. Now, what is cosine of alpha? We find it the other time and we say it is negative 15 over 17. It is negative because alpha itself is in Q3. So cosine is negative there. So that is uh, minus 15 over 17 divided by 2. So that is equal to minus square root of 1 plus times minus 15 over 17 divided by 2 minus square root of 17 minus 15 divided by 17 divided by 2. So that is minus square root of 2 over 17 times 1 over 2. 2 here 1, 2 here 1. So that is minus square root of 1 over 17, which is minus 1 over square root of 17. We can rationalize that. If we do, then it becomes minus 1 over root 17 times root 17 over root 17. And our answer is minus root 17 divided by 17. Lastly, we need to find tangents of alpha over 2. Well, I can go ahead and use this formula here. I can do that. Or I can just use my result for sine divided by my result for cosine, since tangent of alpha over 2 is sine of alpha over 2 divided by cosine of alpha over 2. So which is, for sine of alpha over 2, we have 4 root 17 over 17, 4 root 17 over 17. So divided by cosine of alpha over 2 minus root 17 over 17. So which is 4 root 17 over 17 times minus 17 over root 17. So since I have multiplication in between, this guy will take care of this guy. 17 here 1, 17 here 1. So our answer is 4 times minus 1 minus 4 divided by 1 times 1, 1. So that is minus 4. Answer. So that is how to use half angle. So you can go ahead, pause this video and solve these triads just using the same concept. Make sure you take care of the signs very, very well. Again, just do this. Your alpha here. What is sine of alpha? You've been given. So just do the same thing we just did here. So the next thing we want to look at is solving trigonometric equations. Before this class, you were introduced to trig functions and the fact that you can use these trig functions to model numerous real-world situations. For example, the ocean wave or the tidal wave can be modeled using trig function. For example, we can say the height of the tidal wave is modeled by this. where h is the height and t is the time. So we can ask the question of when, that is the time, when is the height of that tidal wave equals to 5 meters, right? So we can ask that question. We can also proceed to another form of wave, sound wave, for example, which is represented by something like this. Again, we can ask the question of time. For example, we can say solving this equation when it is equal to 0 gives the moments, that is the times, when air particles are at their equilibrium position. Another application is the shadow length of a street light, which we can represent, remember, from your work with SOHCAHTOA, where you say the tree, line of sight. So again, the pole, the shadow it casts, and all those things. So we can represent, or we can model that situation using the tangent function. So in this case, theta is the angle of elevation and x is the length of the shadow of a 3-meter tall street light. So again, we can do some fun stuff with that. So there are some things we need to consider when we are solving this type of problem, because we must remember that trig functions are periodic. That is, we will have infinite number of solutions. They're periodic. Remember, for sine, for example, we have it this way, and it keeps going, right? It keeps going. And also on the negative, it keeps going. So we will have infinite number of solutions. So you must keep that in mind. Again, equations may be solved over a specified interval or for all possible solutions. So we can say find all solutions, or we just say find on some intervals, maybe from 0 to 2 pi, or 0 to 4 pi, or 2 pi to 4 pi, depending on what the situation is. The sine and cosine functions have period of 2 pi. We know that, meaning our solutions will repeat every 2 pi units. We know that. And if it is tangent, the period is pi. So general solutions include adding 2 pi k, where k is an integer to the initial solutions. For example, if I ask, let us quickly remind ourselves some things that we've done in this class. So this is pi, this is 0, this is 2 pi, this is 3 pi, this is 4 pi, and so on. If I ask you to tell me where the graph of sine of x is 0, well, you will tell me it is 0 at 0, it is 0 at pi, it is 0 at 2 pi, at 3 pi, at 4 pi, at 5 pi. In fact, you can also consider the negative part. You can say at negative pi, at negative 2 pi, at negative 3 pi, and so on and so forth, right? So we need to be able to take that into account when we want to write our solution, to account for everything. And to do that, we use the concept of k. For example, if the period is 2 pi, then we say k. Now, since k is integer, we are saying when k is 0, what is it? Oh, it is at 0. When k is 1, it is at what? 2 pi. When k is 2, it happens at 4 pi. When k is 3, it happens at 6 pi, and so on. We will consider examples to establish all these points. I'm just putting that ahead of time. The domain of the function must be considered before validating solutions. Yes. Other trig functions follow similar periodic rules. Yes. Solving trigonometric equations involves algebraic techniques like factoring and substitution. Yes, just like we would do with dealing with algebra. And trig identities can be used to simplify and solve equations. And the unit circle again would be a great use in our work. Let us take example. Find out solutions for the times when the tide reaches 5 meters. So maybe we say when the maybe I should reach it. It's the same thing. When the tide reaches 5 meters, when the tidal wave reaches 5 meters. That is when this equals to 5 from our initial equation. So we do know this is similar to saying solve something like this. It is similar to that. You cannot solve this, right? So that is what we want to do. But now we will account for some things. Pi t over 6 plus 4 equals to 5. So I will say this is 2 sine pi t over 6 equals to, I will subtract 4 from both sides, and here is 1. Right? It is subtracting 4 from both sides. So now I can divide through by 2, then I have sine of pi t over 6 equals to 1/2. Now, at this point, recall our work when we're dealing with inverse of trig function. If I give you sine of some angle equals to 1/2, and I say, what is x? I'm asking you, what angle is it that when we take the sine of that angle, it is half? And then we say, well, for the sine, it is pi over 6, and also 5 pi over 6. Now, I'm looking for all possible solutions, all possible solutions. So I would say pi c over 6 is pi over 6, or pi t over 6 equals to 5 pi over 6. Now, those are the two places in one rotation, in one period, where that pi t over 6 equals to, where the sine of pi t over 6 equals to 1/2. But recall that we have infinite solutions. We have many solutions. That is, it goes beyond one period. It keeps occurring. It is periodic. Now, this is what I'm going to do. I'm going to say this pi over 6 equals to pi over 6. Pi t over 6 equals to pi over 6. We occur when I add or subtract 2 pi k. It is going to be half when I add 2 pi k at every instance. When I add 2 pi k or I subtract 2 pi k, that is plus 1 period every time. Okay? Now, the same thing with this, we will come back to that. Now we are looking for, if our question is saying we should look for our answer on this region, 0 less than equals to t less than equals to, let's see, say our answer, we just want our answer to be here, because that is angle. Let me say I want my Yeah, I want pi c over 6 to be between 0 and 2 pi. Then I'm okay with pi over 6 and 5 pi over 6 because that is within one period. But because we are looking for all solutions, so I need to consider that every period I'm adding to it. So now in this case, I can say, well, let me multiply this by 6 over pi so that I will have just t. So again, I will multiply also this side by 6 over pi. So what do I have? 6L1, 6L1, pi L1, pi L1. So I have t equals to, if I multiply this, I will have pi over 6 times 6 over pi plus or minus 2 pi k times 6 over pi. And this is 1 plus or minus pi will take care of pi, so that is 12k. So that is, it is going to happen at 1 hour, then plus or minus 12k. So remember, so we can say where k is the set of integers. However, our time is always positive. So I'm going to consider just the positive integers, right? So, um, so now that is t equals to 1 plus 12k, where k is positive integer. So when I can start, when k is 0, it is 1 hour. When k is 1, 13 hours. When k is 2, that is 12 times 2, 24 plus 1, 25 hours. So that is how it happens. 1 hour, the next one is at 13 hours, the next one is at 25 hours, the next one is at, that is 3 times 12, 36 plus 1, 37 hours. So you can see just plus 12, plus 12, plus 12, plus 12. If you have been to Yellowstone before, um, I've been at the one in Montana, and there is some occurrence with the bubbles that come from the ground, and they will tell you that this will happen at so time. So they are able to tell you the time it will happen. So you see people standing and waiting for that time. And exactly at that time, it is going to happen. You see the boiling or hot um, liquid coming from the ground and throwing up and coming back to the ground. The reason they could do that is because they were able to use trig function to model that situation. And because it is periodic, we can generate the time infinitely. And so if the first one happens by 1 o'clock, let's say 1 p.m., then you know that the next one is going to happen, 12 hours later. So you can tell someone that come exactly at this time, that is when it's going to happen in that case. But don't forget, that is not the only solution. We still have 5 pi over 6. So we also need to consider that. So also, so we use that of one rotation to figure out all possible solutions. So we say also, pi t over 6 equals to 5 pi over 6 plus 2 pi k. Again, I will not use negative because I'm only considering positive integer. or let me say I'm considering time, which is positive. So now, again, I will do the same thing. So very fast now, I will multiply both sides by 6 over pi to get rid of that pi over 6. So equals to 5 pi over 6 plus 2 pi k multiplied by uh, 6 over pi. So if we do that, we have t equals to 5 pi over 6 times 6 over pi plus 2 pi k times 6 over pi. And we have that t equals to, so pi will take care of pi, 6 will take care of 6, so we have 5 plus, what's that? Pi will take care of pi, so that is plus 12k. So what we can say here is that the tide will reach 5 meters at t equals to 1 plus 12k and 5 plus 12k, where k belongs to the set of positive integer, including 0. So when k is 0, the first one will happen at 1 and 5 hours. So maybe one happen at 1 p.m. You are sure that another one will happen at 5 p.m. Now, plus 12, you know that after one period for that, you have another one happening at 12 hours added to that 1 p.m. Right? And then you add 12 hours to this. So you know that another one is going to happen at that time, and it continues that way. So that is why you can approximate, tell people when such periodic events will take place. This is a lot going on there, but it is just, you know, um, our ability to recollect our work with the unit cycle and to account for the fact that we are looking for time, and also that we have infinitely many solutions. So we need to account for everything. So that is that. Let us take another example. Solving 0.05. This is the other situation we have, whereby we say sound wave displacement. That is when the air particles will be at equilibrium. That is when that function equals to 0. Again, we do the same thing. So 0.05 sine of 400 pi t equals to 0. So we can divide through by 0.05, so that is sine of 400 pi t equals to 0, right? We are asking the question. So if I give you something like this, sine of x equals to 0, what is x? I'm asking, what angle x is such that when you take the sine of that angle, it is going to give you 0? Remember, from our unit circle, we have 1, 0, here 0, 1, here negative 1, 0, and also uh, 0, negative 1. So sine is 0 at this point, because we can have it here, we can also have it here. So that is at 0 and at pi, right? So that implies that 400 pi t equals to 0 and 400 pi t equals to pi. I hope that makes sense to you. Because here I will just say, well, my x is 0, comma pi, right? But then I know there is going to be repetition when I add or subtract 2 pi, add or subtract 2 pi. Because that is not the only one I will add. I have many of them. Then I need to put k to account for many. So the same thing. So for all solution now, for all solution, we need to find where 400 pi t equals to 0 plus, again, we are dealing with time, so 2 pi k, and where 400 pi t equals to pi plus 2 pi k. We are dealing with time. So let us solve this part. I can divide through by 400 pi, right? So that is 400 pi t divided by 400 pi equals to 0 plus 2 pi k divided by 400 pi. So this implies that we will have t equals to 0 over 400 pi plus 2 pi k over 400 pi. You don't have to do it gradually as I'm doing. This is just for explanation's sake. So this is 0 plus pi, we take care of pi, 2 here 1, 2 here 200. So that is 1 over 200k. So which is 1 over 200k. That is the first time when it will be at equilibrium. Also, for this, we divide through by 400 pi. So that is t now equals to pi over 400 pi plus 2 pi k over 400 pi. So which is 1 over 400, because pi will take care of pi, 1. So 1 over 400 plus pi, 2 here 1, 2 here 200. So 1 over 200k. So we can conclude that what is the question? Solving this gives the moments when air particles are at their equilibrium position. So we can say the air particles are at equilibrium positions at times t equals to 1 over 200k and 1 over 400 plus 1 over 200k, where, well, the unit is hours. Hours, where k belongs to the set of positive integers. So, guys, that is how to deal with a situation like this. It's a lot, but that is how we solve real world problems. So in general, let us Okay, I have a problem where I give you just from 0 to pi. So let us quickly solve this. Again, if I want to solve this, I need to use some identity. So this is 2 sine of x plus 1 over sine of x equals to 0. Uh, I can, what can I do? I can multiply through by sine of x. I can multiply through by sine of x, and that means I will have 2 sine squared of x. That is, I can multiply everything by sine of x. So that is 2 sine squared of x plus 1 equals to 0. And I have 2 sine squared of x equals to negative 1. Sine squared of x equals to negative 1 over 2. And I have sine of x equals to plus or minus square root of negative 1 over 2. Well, here we can say there are no real solution because we don't want to take, we cannot take the square root of negative 1 half. So we say no real, that is real numbers, real solution. Whatever, wherever in the future we are able to do that, we must also exclude, we must also exclude points where sine of x equals to 0. Why? Because we cannot divide by 0, which is what we have from from cosecant of x, because it is 1 divided by sine of x. So we should also remove those points. And that would be, that is, where x equals to 0, comma, pi, comma, 2 pi, and so on, which implies point where x equals to, so we have 0, pi, 2 pi, 3 pi, so I can just say where x is pi k, where k is in the set of integer. Uh, oh, well, we are looking for a solution on 0 to 2 pi anyways. Well, so we can say, we can just stop here. We can just stop here. So, because we are restricted. So we can just stop there. And 2 pi. So we can just stop there. But for this itself, we do not have real solution there. So we just leave it at this. But if for some reasons we are able to find a way to do something to that, we also know that we still need to exclude where sine of x is 0. That's some fun example. Okay, here we want to find all solutions. Looking at this, it feels like we can represent this in terms of quadratic. So here I can say let P represent sine of x. That implies that this will become 2p squared plus 3p plus 1 equals to 0. I can factor that. I can factorize that. So that is 2p squared plus 2p plus p plus 1 equals to 0. You should know how to factorize by now. So that is 2p into p plus 1 into p plus 1 equals to 0. So we have 2p plus 1, then p plus 1 equals to 0, which implies that 2p plus 1 equals to 0, or p plus 1 equals to 0. And we have that 2p equals to negative 1, and p equals to negative 1 over 2. So p equals to negative 1. So we have two situations. We need to pick that one by one, just like we did in our real world example. So we say when p equals to negative half, our p is sine x. That is, sine x is minus 1 over 2. Now, guys, we are asking, what is that angle such that when we take the sine of that angle, it is negative 1 half? We'll return to our unit circle, negative 1 half for sine. Not here. We have it here, 7 pi over 6, and also at 11 pi over 6. So we have it, that is, x is 7 pi over 6 and 11 pi over 6. Now, since we are looking for all solutions, remember, this 2 is just in one rotation. So for all such solution now, it implies that x is 7 pi over 6 plus or minus 2 pi k, and 11 pi over 6 plus or minus 2 pi k. So we've accounted for all the solutions for when sine of x will be 1 half. Similarly, we consider when p equals to negative 1 here. That implies we want to find when sine of x, remember p is sine of x, equals to negative 1. That is, we are asking, what is that angle such that when we take the sine of that angle, it is negative 1? In the unit circle, let's quickly return to that. When is sine negative 1? Not here, not here, it is here. You see? Sine is negative 1 there, so that is at 3/2 pi. So that happens at just that one point. That implies that x equals to 3 pi over 2. That is where it happens. Now, to account for every other solution now, outside that one rotation, it implies that x equals to 3 pi over 2 plus or minus 2 pi k, since the period of sine is 2 pi. That k there is telling us that, when k is 0, when k is 1, when k is 2, and so on. Therefore, our solution x is 7 pi over 6, 7 pi over 6 plus or minus 2 pi k, 11 pi over 6 plus or minus 2 pi k, and 3 pi over 2 plus or minus 2 pi k, where k belongs to the set of integers. Okay, let us solve Let me see. Let us solve this example. Oh, I like this example. Solve the equation exactly using double angle formula. Well, what is the double angle formula for cosine of 2 theta? Since I have theta here, maybe I should use the one that is having cosine. So recall that cosine of 2 theta is 2 cosine squared of theta minus 1. So I can replace this using this identity. So equals to cosine of theta. And I can bring cosine of theta here, minus 1 equals to 0. So again, we have the kind of situation we have the other time. So I can say let P be cosine of theta. So we have 2P squared minus P minus 1 equals to 0. So we can solve this. 2P squared, 2 times 1, 2 minus 2P plus P minus 1 equals to 0. 2P into P minus 1 plus 1 into P minus 1 equals to 0. So 2P plus 1, P minus 1 equals to 0. And then we have 2P plus 1 equals to 0, or P minus 1 equals to 0. And from here, P equals to negative 1 over 2, or P equals to 1. So we take this situation one by one. When P equals to negative 1 over 2, that is, or that implies when cosine of theta equals to negative 1 over 2. So we are asking, when is the cosine of some angle equal to minus 1 over 2? That is, what is that angle? Such that when we take the cosine of that angle, it is negative 1 over 2. And we'll return again to this. Negative 1 over 2 for cosine. It happens here, 2 pi over 3. Happens here for pi over 3. 2 pi over 3 for pi over 3. So that implies that theta is 2 pi over 3 and 4 pi over 3. Since we are looking for the solution between 0 and 2 pi, that is just one rotation, then I will not bring in plus 2 pi k because I've already found my answer within that 0 to 2 pi. Also, when p equals to 1, it implies that cosine of theta is 1 there. We are asking, what is that angle such that cosine of that angle is 1? Again, if you don't know it offhand, we return here. When is x 1? X is 1 when it is 0. It's negative 1 there. And again, when it is 2 pi. So at 0 and at 2 pi. So that implies that theta is 0 and 2 pi. And again, that is the answer. Therefore, our solution is theta equals to 0, 2 pi over 3, 4 pi over 3, 2 pi. So that is our answer. We are only looking for solutions within 0 and 2 pi. So done. So you have a couple of problems to solve here. So just pause this video and play around all these problems here and see what you can do with that. That shouldn't be problematic at all. I'm going to stop this video here. Oh, okay. I don't want the video to be too long, but let me quickly finish this because it's almost over anyway. So this is just using calculator. Using calculator. Use the calculator to solve the equation. There is a reason why I want to do this with you. So grab your calculator and let's see something. Use the calculator to solve the equation sine of theta equals to 0.5 where theta, you need to, where theta, let me just write this there, where theta is in radians on 0 less than equals to theta less than equals to 2 pi. Well, let me do something. Let me say 360. I want to show you in degrees first. It's in degree, right? Okay. Now we say sine of theta equals to 0.5, which is 1/2. I know you can do this without calculator, but I want to show you something. Now, if you say theta is sine inverse of 0.5, which is true, right? From our work on inverse of trigonometric function. And you say theta is, if you go to your calculator and you go to um, second function, make sure your calculator is in degree. I want to work in degree. So if I go to sine inverse of 0.5, it's going to give me 30 degrees. So you notice that calculator is just going to give you one answer. And that is because calculator is restricting our answer to the restricted domain of sine, which is negative pi over 2 to pi over 2. So calculator is going to pick answer here. So it's just going to supply one answer. However, for the entire rotation, we know that there is one angle that we can find also on the other side. How can we get there? For this, it is simple. You can even tell me what it is. I know, but let us look at this. Now, calculator is giving us 30 degrees. Okay, 30 degrees. I do know something that the ratio I'm having here is positive. Okay. Now, where is sine positive? In the first quadrant and in the second quadrant. So I do know that the second angle will be somewhere here. And that 30 is, so I need some angle before that from here to here, right? Now I can talk about reference angle between this terminal point and the horizontal axis. Now that 30 could be considered as the reference angle here, right? So that is from this to this point will be 150 degrees. Or you say 180 minus 30 degrees, which is 150 degrees. So I do know that all the solutions between 0 and 360 degrees will be 30 degrees and 150 degrees. Okay. So that is why I'm using calculator, just to show you that when you are looking for all solutions, calculator is just going to give you just one because it is restricting it to the restricted domain for sine. So what about this now? Let us work in radians now. So we do the same thing. Um, so I'll be faster now. Sine theta equals to 0.8. So theta is sine inverse of 0.8. So theta is, so I will make sure I'm working in radians. So sine inverse of zero point 0.8. That is 0. I say it is approximately equal to 0.9273. So meaning that I have something like this. So let me show you this. Remember, this is 0. Here is pi over 2, which is the same thing as dividing pi into 2, which is 1 point. Here is 1.5708 approximately. Here is 3.142, that is pi. And here is, so that is 3 pi divided by 2. So that is 4. This place is 4.7124. And here is also 2 pi. So which is 2 pi. That is 6.2832. Okay, in decimal. All right. So now our angle theta is approximately 0.9273, which means it is somewhere here, right? I know that since this value is positive, the second one is going to be here for sine. So all I need to do now is to say the second one is pi minus 0.9273. So which is 0.9273, comma, pi minus 0.9273. So that is 2.2143. Let us try to cross-check. Let us find sine of 2.2143. Okay, I have 0.7999, so that is 0.8 approximately. So we are correct. Yeah, I know it is tricky to use calculator, and that is because calculator only gives us one. Okay. So you can go ahead and do this, try it. Solve this, try it. I will stop there for now. We will consider this last example together in class. So let me stop that video for now. Okay, I will see you guys in class. Just take your time and go through what we have. It is, you know, pretty straightforward. It is pretty straightforward. So starting from um, reduction formula or through solving that. Okay, so bye guys. I will see you in class.